Hello students, in this lecture I will discuss about the N-Slit Fraunhofer diffraction pattern. In the last lecture we have discussed about the double slit Fraunhofer diffraction pattern. So the number of slits now increased from 2 to n, and then I will discuss about the grating spectra. Okay, let's move on. Let us suppose that this is n number of slits in a system. We have a n number of slits and n number of parallel slits, and each slit is of width b. So this separation is b, and the center to center distance is a. So this separation, center to center distance, is a. So we have n number of parallel slits, each of with b, and the center to center distance is b. So to find the procedure for finding the irradiance function for a monochromatic wave diffracted by these n number of slits is essentially the same that we have used in the last section, that is for the two slits, that is the double slit. But here we have to choose the proper limit of integrations, and the total optical disturbance at a point on the screen. Let us suppose this is a point on the screen, this is a point P on the screen. So at this point this optical disturbance can be obtained by using the relation E is equal to E naught. So the integration from minus b by 2 to plus b by 2 that we have seen in the single slit diffraction phenomenon, and for the next integration limit will go from a minus b by 2 to a plus b by 2. For the double slit we have seen also this limit of integration. So the limit will change in this manner. The next one will be the integration from minus 2a minus b by 2 to 2a plus b by 2, and it will go till integration n minus 1 into a minus b by 2 to n minus 1 a in plus b by 2 to the power ikz into dz. So by integrating we will get this expression. This expression will come after the integration, which includes a constant sin beta by beta and sin n alpha by alpha. So the integration, so the intensity will be I equal to I naught sin square beta by beta square into sin square n alpha by alpha square. So you can see that here we have two terms. One is sin square beta by beta square, and the other one is sin square n alpha by sin square alpha square. So the intensity distribution function is a product of two terms. The first term is sin square beta by beta square, which represents a diffraction pattern produced by a single slit, that we have seen in the last lecture. And the second term, which consists of sin square n alpha by sin square alpha, represents the interference pattern term by n equally spaced point sources. Let us illustrate the second term, why it is termed as the interference term. For that, let us take n is equal to 1. For n is equal to 1, we will get at the value of I, that is intensity distribution, will be I is equal to I naught sin square beta by beta square. So this is the expression for single slit. So this is the expression for single slit. Now let us take n is equal to 2. So for n is equal to 2, we can write I is equal to I naught sine square beta by beta square. Then for n equal to 2, we can write sine square 2 alpha by alpha square, and sine 2 alpha is equal to, we can write 2 sine alpha cos alpha. So sine square alpha cancels out, and the 2 square will give 4, and cos square alpha remain there. So the expression for I is now 4 I naught sine square beta by beta square cos square alpha. This is the expression that we have got in the case of double slit diffraction pattern. So the second term in the expression, so this term is for double slit. This term for this is for double slits. For n equal to 2, that is number of slit is 2. So the second term in the expression for the intensity distribution gives the cos square alpha, which represents the interference term in the double slit pattern. So you can say that the second term, that is this term, you can say this term represents the interference pattern produced by n equally spaced point sources. Okay. Now when theta is equal to 0, I, let us write I function of 0 is equal to, that comes n square I naught. Thus, that is the waves arriving at P, that is on the screen, are all in phase, and the fields of all the waves are added constructively. And if the if B tends to 0, if B shrinks to 0, that is the width of the slit is nearly equal to 0, that means the slits are very narrow, the flux density would become the flux density expression for a linear coherent array of oscillators. Okay. So we have the intensity distribution for n slits is equal to I naught sine square beta by beta square into sine square n alpha by sine square alpha, that we have seen in the previous slide. The intensity would be maximum when this term is 1. So it would be 1 when sine alpha is equal to 0, also sine n alpha is equal to 0. Sine alpha is equal to 0, that means alpha has the value plus minus m pi, and sine n alpha is equal to 0, that means this term 0 by 0, it is undetermined. So to find the value, we need to use this method, limit alpha tends to plus minus m pi, that we have got from this condition, sine n alpha by sine alpha. So limit alpha tends to m pi plus minus m pi, differentiating numerator and denominator, so get n cos n alpha by cos alpha. So this comes plus minus n. So the intensity pattern, intensity expression, the expression for intensity distribution can be written as I equal to a square, if a is a constant, sine square beta by beta square into n square. So this is the intensity of principal maximum, because we have considered it will be, the intensity would be maximum. So this gives the intensity of the principal maximum. Also we have considered that alpha is equal to plus minus m pi when sine alpha is equal to 0. So we have alpha is equal to plus minus m pi. Alpha is equal to, we know from the last lecture that alpha is equal to pi by lambda a sine theta m. So this is equal to plus minus m pi. So we have got the expression a sine theta m equal to m lambda, where m has the value 0, plus minus 1, plus minus 2, plus minus 3, etc. So we got an equation which is a sine theta m is equal to m lambda. as the maxima exist, so there must be minima also there. So minima exist whenever sin n alpha by sin alpha is equal to 0. Sin alpha cannot be 0 because it will give the position of principal maxima. So sin n alpha must be equal to 0. If sin n alpha is equal to 0, so we can say that n alpha is equal to plus minus n pi. Or alpha is, oh, here it is alpha. This is the value of alpha. Alpha is equal to plus minus pi by n, putting n is equal to 1. Pi plus minus pi by capital N plus minus 2 pi by capital N plus minus 3 pi by capital N. Then n minus 1 pi by n. N is equal to n will not be possible because that gives pi. Pi is the position of the principal maxima, and then the n plus 1 into pi by n. So, thus between consecutive principal maxima, that is over the range in alpha of 0 to pi, there will be n minus 1 minima. Let us suppose this is the position of pi by n. The previous position is pi alpha is equal to 0. So, alpha is equal to 0 is the position of principal maxima, and then the value of pi increases, and this is the position of n is equal to n. So, n equal alpha is equal to pi. So, n equal alpha is equal to 0 and alpha is equal to pi. These are the position of principal maximas. So, in between there, these are the positions of minimas. So, we have 1, 2, 3, 4 up to n minus 1 minimas. So, in the between the consecutive principal maximas, in the range of range in alpha of 0 to pi. So, 0 to pi we have n minus 1 number of minimas. As there are n minus 1 number of minimas, just move. Let us suppose this is a these are the principal maximas, and this is for n is equal to 6. The number of slits are here 6. So, if it is n is equal to 6, then the number of minimas must be n minus 1, that is 5. So, we have between two principal maximas, we have 1, 2, 3, 4, 5. So, n minus 1, that means 5 minimas are there. For n equal to 6, we have 5 minimas between two principal maximas. Then there must be 4 maximas, that is 1, 2, 3, 4. So, there must be 4 maximas, that means n minus 2 number of maximas between two principal maximas. And these n minus 2 maximas between maxima between two principal maxima termed as subsidiary maxima or secondary maxima. So, we can say that these are the principal maximas and these are the subsidiary maximas. The subsidiary maxima are located approximately at points where sin n alpha has its greatest value. The sin n alpha has its greatest value. At that point, we will get the subsidiary maximas. So, sin n alpha will be maximum when n alpha will be equal to plus minus m pi by 2. So, the value of alpha is equal to 3 pi by n 2n, 5 pi by 2n, and so on. This gives the position of n minus 2 subsidiary maxima between consecutive principal maximas. Now, rewrite the equation. We can rewrite the equation as I function of theta is equal to I function of 0 by n square sin beta by beta square and sin n alpha by alpha whole square. At subsidiary maximas, the value of sin alpha, modulus of sin alpha is equal to 1, And for large n, alpha is small and sine square alpha can be considered as alpha square. At first subsidiary peak, we have alpha has the value 3 pi by 2n that we have got in the here, that the first subsidiary maximum we have alpha has the value 3 pi by 2n. So putting this 2 by 3 pi square, you can calculate that the flux density, that is I by I naught, dropped about 1 by 22 of the adjacent principal maximum. For that, this is the reason that you can see that this is the principal maxima of intensity n square, and the intensity of the next subsidiary maxima is so much less than the principal maxima, which is nearly 1 by 22 of the principal maxima. And if you calculate for the next one, that means next subsidiary maxima, then the ratio of the flux density or the intensity of the next secondary subsidiary maximum to the central maximum is down to 1 by 62, and it continues to decrease. It continues to decrease as alpha approaches a value approaches a value halfway between the principal maximas. At that symmetry point, that is the midway between the principal maximas, that is at alpha is equal to pi by 2, sine alpha is equal to 1, and the flux density ratio has the lowest value, which is approximately equal to 1 by n square. So at the symmetry point, alpha equal to pi by 2, the density ratio would be nearly equal to 1 by n square, which is the lowest value. Okay, now we have the equation principal max. We have that the principal maximum occurred at a sine theta m is equal to m lambda, and minima occurs at alpha is equal to plus minus pi by n plus minus 2 pi by n, then dot dot n minus 1 pi by n, n plus 1 pi by n, and so on. If theta m plus delta theta 1 m and if theta m minus delta theta 2 m represents the angle of diffraction corresponding to first minimum on either side of the principal maximum, that is the first minimum. Let us suppose it is the principal maximum. So this is the first minimum, and on that side we have the other first minimum. So if theta m plus delta theta m and theta m minus 2 delta theta m, delta theta 2m represents the angle of diffraction corresponding to the first minimum on either side of the principal maximum, then half of theta delta theta 1m plus delta theta 2m is known as the angular width of the mth order principal maximum. For large value of n, we can say that delta theta 1m is nearly equal to delta theta 2m, and a sine theta m plus minus delta theta m is equal to m lambda plus minus lambda by n. So sine theta m plus minus delta theta m, we can write this is equal to this expression, and sine theta is equal to sine theta m plus minus delta theta m cos delta theta m. So putting these in this expression, we can get the value of delta theta m is equal to lambda by n into a cos theta m, which is the half angular width. This expression shows that the principal maximum becomes sharper as the value of n increases. So, the width of the principal maximum is equal to 2 lambda by Na. Now, come to grating spectra. The a repetitive array of diffracting elements, either apertures or obstacles, that has the effect of producing periodic alterations in the phase, amplitude, or both of an emergent wave is said to be a diffraction grating. That is an arrangement which consists of a large number of equidistant slits, and the corresponding diffraction pattern is known as the grating spectrum. This is achieved by ruling groups with a diamond point on an optically transparent sheet of material. The groups or rulings act as opaque spaces. In reality, most gratings are the replicas of these fine master rule gratings made on good quality plastic or glass. Nowadays, gratings are also made by made holographically. We have the expression that we have a sine theta m is equal to m lambda. This equation is known as the grating equation of normal incidence. This equation dependent on lambda, and the value of m specify the order of the various principal maxima. This equation is dependent, and the value of m is 0, 1, 2, and so on. This equation is dependent on lambda. M equal to 0 gives the 0th order at theta equal to 0 irrespective of the wavelength. For m not equal to 0, the angle of diffraction are different for different wavelengths, and therefore various spectral components appears at different positions. Thus, by measuring the angle of diffraction for various colors, we can determine the wavelength using the proper order of the diffraction. That is by using the proper value of m, we can find the value of lambda by measuring the values of theta. Now, differentiating the equation, we get the expression delta theta by delta lambda is equal to m by a cos theta m, which is termed as angular dispersion. For small theta, cos theta is nearly equal to 1. So, delta theta is proportional to m. So, for a particular delta lambda, which is for a particular, if we consider delta lambda as is constant, so this means that the angular separation between two different frequency lines will increase as the order increases. So, as we increase the order, that is the value of m, for a particular lambda, the angular separation will increase. Thus, delta theta, delta lambda is constant for a given m. Also, delta theta is proportional to delta lambda for a given m. That is, the difference in angle of two spectral lines is directly proportional to the difference in wavelengths for small theta. For large theta, the dispersion is greater at the red end of the spectrum, and delta theta is proportional to 1 by A. That is, delta theta is inversely proportional to the grating element. Thus, smaller the grating element, larger will be the angular dispersion. This is an arrangement. Let a parallel beam of light emerging from a slit placed at the focal plane on the lens of the lens L1. This is the lens L1. Falls on the grating, and the diffraction pattern. This is the grating. So the light coming from the slits, which is the slit is placed on the focal plane of the lens L1, crossing the lens L1. It falls on the grating element, and the pattern, diffraction pattern, is observed on the screen which is placed at the focal plane of L2, and the diffraction pattern is viewed through an eyepiece. The angle of diffraction for various orders of grating spectrum can be measured, and by measuring the value of A, that is the grating constant, one can calculate the wavelength of different spectral lines. This is the picture of a grating spectra, which you can see in the laboratory. This is the number of slits, and these are the different orders, that is the number of maximas and minimas as changes with the number of slits. So resolving power of a grating, R, is defined as lambda by delta lambda minimum. It is the power of the grating to distinguish two nearly spectral lines, where delta lambda is the least resolvable wavelength difference and lambda is the mean wavelength. Delta lambda is the separation of two wavelengths which the grating can resolve. That is, smaller the value of delta lambda, the larger the resolving power of the grating. According to Rayleigh criteria, if the principal maximum of corresponding to wavelength lambda plus delta lambda falls on the minimum of the wavelength lambda, then the two wavelengths lambda and lambda plus delta lambda are said to be just resolved. So this is the principal maxima of lambda plus delta lambda. Principal maxima of the lambda plus delta lambda falls on the minima of the, actually this image is okay, it falls on the minima of the lambda, then the wavelengths are said to be just resolved according to Rayleigh criteria. And if the angle of diffraction common for both the wavelength lambda and lambda plus delta lambda be theta for the order of spectrum m, and then we can write A sin theta is equal to m into lambda plus delta lambda, and also A sin theta is equal to m lambda plus lambda by n. Here n is the number of slits on the grating. So lambda by delta lambda can be written as, from these two equations, lambda by delta lambda is equal to small m into capital N, where small m is the order and capital N is the number of the slits on the grating. So this gives the value of resolving power. So the resolving power of a grating depends on the number of lines and the order of the spectrum. That is, the resolving power of a grating will increase indefinitely if n is increased. But for a given width of grating, if the width, actually the width is constant for a grating, so this is equal to n, capital N, in multiplied by A, because A is the grating element, and n is the number of slits. So n into a gives the value of the width of the grating, capital D. So for a particular value of D, uh, as n increase, if we increase a, then the value of a will decrease. Thus the maximum value of n, value of m also decreases. So that's all for today. Thank you for watching.